In this lecture, we're going to do the first proof that we have done in MAT 103. We're going to prove that there are infinitely many prime numbers. That's probably what most of you would guess, that there are infinitely many. But really, how do you know? I'll show you later in this lecture the largest prime that we know of so far. How do we know that there's another one after that? Why would universities spend a lot of money searching for the next biggest prime unless they knew that it really existed? So that's what we will do today, is prove that there always is another prime number after the biggest one we know of. You have already looked at numbers like this in class in preparation for understanding the proof that we're going to do now. And I'd like to look at them one more time. If you have a number like t, which is 1 times 2 times 3 times 4 times 5 plus 1, in other words, you multiply these numbers together, multiplying first, and then you add 1. Actually, what you get, this one's easy to just multiply out, you have 121. That's the number. Now, we write it in this more complicated way because when we write it this way, we can see that 2, 3, 4, 5, and many more factors. 2 times 3, 6, 3 times 4, 12, 2 times 4, 8, 3 times 5, 15. Any combination of these four numbers multiplied together, those are factors of this number right here. They are not factors of t, because when we add 1 at the end, we guarantee that if you, for example, take this number 121 and you divide it by 5, let's say, any one of these numbers, same thing happens. Well, we get 2 and then 10 and 2, bring down the 1, and you get 4. 4 times 5 is 20, and there is our remainder of 1. And it was funny in class because most of you have just used calculators for so many years, you've forgotten all about this process that I learned in the 4th grade. This means 121 is equal to 5 times 24 plus the remainder of 1. So if you divide t by 2, 3, 4, 5, 20, 12, 6, 12, 2 times 5, 10, any combination of these four numbers, if you divide t by that, you will always be left with a remainder of 1. So none of the numbers less than or equal to 5 are factors of t. Note here that t is 121. It's not divisible by 2, 3, 4, or 5 or any of their products, but notice that doesn't mean that t is prime. In fact, 121 is equal to 11 squared. So just because none of these factors divide t, it certainly does not mean that t is a prime number itself. And the same goes for all of the numbers that we build this way. Let's take one more slide on this before we start the proof. What numbers, meaning natural numbers, do you know for sure do not divide the numbers m and s that you see here? First, look at m. Notice it says we are multiplying all the natural numbers together, less than or equal to 5 million. And then we're just going to add 1. That's what m is. By adding the 1, we guarantee that 2 does not divide m. 3 is not a factor of m. 4 is not a factor of m. 5 is not. 6 is not. 7 is not. And in fact, all numbers less than or equal to 5 million do not divide m. If you divide m by any of these numbers, there will be a remainder of 1. So let's see, no natural number, other than 1 of course, no natural number less than or equal to 5 million divides or is a factor of the number m. Down here it's a tiny bit more abstract. Instead of having a number, we just have n here. N just stands for a natural number. Any natural number. It doesn't have to be 5 million. If you have a number s written as the product of all of the natural numbers less than or equal to some number n, and then you add 1, you can say that s cannot be divided by any of the numbers up to and including n. So all numbers less than or equal to n are not factors. Factors of the number s for any natural number n, and you're assuming it's when you write it this way, 1 times 2 times 3 times etc. up to and including n, you're kind of assuming that n is bigger than 3. But if n is 4, this is just 1 times 2 times 3 times 4. If n is 5 million, then this s is the same thing as this number up here. Now, you, after we ask this question, put it on pause and see if you can think of exactly what this means about prime numbers. If we can prove that given any prime number, capital P, no matter how big it is or how small it is, given any number, prime number P, there is always another prime bigger. What will that mean about the set of prime numbers? You think about it and put it on pause right now and see if you can think of what that means. Okay, well, hopefully you said that it means if this is true, if this can be proven, then we will be sure that there are infinitely many primes. If there's always one bigger, then there are infinitely many. There's no end. Think about it. If there's always one bigger, then there is no biggest, and therefore there has to be infinitely many. Make sure that that makes sense to you. This is just for your interest. You certainly don't have to memorize this number or anything. But to date, as of today, the largest known prime number is this one right here, 2 to the 57,885,161. 2 to that power. Remember what 2 to the 50th was? If we stacked paper, it would go to the moon over 200 times. Well, think of how big this number is. It's much more than we can imagine, but it is a prime number if you subtract 1. These are called Mersenne primes. Mersenne primes are of the form 2 to a power minus 1. Lots of these numbers turn out to be prime. Not all, of course, but lots of them do. And this was done in a Mersenne Prime search, an internet search. I think it was about 1990. In the 1990s, this great internet Mersenne Prime search was started with the advent of the internet, and it's, so available to us. This number has 17,425,170 digits. And in order to find this number, it took 360,000 central processing units, peaking at 150 trillion calculations per second. I thought that was really amazing. But again, this is not, you're not going to be tested on this. I just thought you might be interested. So now we'll start the proof. Let capital P, in your text he calls it big prime, but we'll just call it capital P, be a prime number. You could assume if you want that it's really, really big, maybe even the biggest ever found. But it stands for any prime. And let's create a new number, capital M, which is even bigger than P. M is, right here, M is the product of P and all natural numbers less than P. Multiply them all together and add 1. So there's two things you have to notice. One is that M is much, much bigger than P. We don't know if M is prime or not prime, but we know that it is much bigger than P and that it has none of these factors. So just to make sure that you see that, let's just say that we chose little p equal to 7, and we make this number m, little m, and let's call it 1 times 2 times 3 times up to times 7, and add 1. If you multiply that out on your calculator, actually you don't need to know this, but some of you have seen it before. It's 7 factorial plus 1, that's on your calculator, and you will get 5,041, I think. Let's check. Yes, you can get that on your calculator. It's 5,041. So just see, if you pick a value of p and you use it to create this new number, it's way bigger than just that last factor in the product there. So m is always much, much bigger than p. And keep in mind, m might be prime, it might not be prime. But if it's not prime, we know that it doesn't have any factors less than or equal to p, so any of its prime factors are going to be bigger than p. And that's down here. Can you see that no number less than or equal to p is a factor of m? Okay, well here's m written out like it was on the last slide. And we learned this fact at the beginning of this section 2.3 in the text about prime numbers, that m is certainly a natural number, and it is either prime or not prime. Now, if it's not prime, it is a unique product of prime numbers. In other words, m can be prime factored, as we've been doing in class. So m is either prime or it is a product of primes. M, the big number. Okay, so well, let's take the first case. If m is a prime number, we know it is bigger than p. We just said before, we showed it with p equals 7. If m is a prime number, we know it is bigger than 3, comma, so we have found a prime number larger than p. So if it's a prime, we're done. We found one bigger than p. That's what we're trying to do, is prove that given a prime p, there's always a bigger one. So that's case 1. Now, case 2, if m is not prime, then it has a prime factor. It might have many of them. It has prime factors, but let's just say it has a prime factor, and let's call it, why don't we call it little q? If it's not prime, it has a prime that divides it, and we only need one. So let's just take q. Q divides m. Q is a factor of m, and q is prime. But we know that q is greater than p. This is important. Q is also greater than P. Now, put it on pause if you need to and look up at M and tell yourself why. If M, this huge number, is not prime, it has a prime factor. How do you know that the prime factors of M are all larger than P? Well, it's because of how we prepared ourselves to be able to understand the proof. And let me write, this is because we created M so that no number less than or equal to capital P divides it. So it has a prime factor greater than P. So in either case, we have proven that there is, given any prime capital P, that there is a prime greater than P. And that's really the end of the proof. Now on the next slide, I'll just review the proof. If you're going to write the proof up, you don't have to have all of these examples, and it's a very short proof. So here is the proof the way that you would write it formally. And of course there's more than one way, but there are infinitely many prime numbers. Proof. Let P be a prime number, and make the number capital M to be the product of P and all numbers smaller than P, natural numbers, and then add 1. M is either prime itself or M is a product of primes. If M is prime, case 1, if M is prime, then we've found a prime bigger than P, because M is bigger than P. Just put that in parentheses. M is certainly much bigger than P. And case 2, if M is not prime, then it has a prime factor, say Q. The way that we created M allows us to say, since no prime less than or equal to P divides M, Q must be greater than P. So we get Q greater than P. In either case, then, we have found a prime number bigger than P. Thus, no matter what prime we choose, there is always a bigger one. We can thus conclude that there is no biggest prime, and thus there are infinitely many primes.